Hello, Java programmers. Let's talk about multi-threading, parallel programming, parallel processing, concurrent programming, all of which mean roughly the same thing. First, we'll define some terms to help us all talk the same language. A program sits on a mass storage device like a hard drive or an SSD. It contains a set of instructions for the CPU to follow. It could have been built from a Java app or a C# app, or even if you take the right steps, a Python app, but it is not human readable. In a Windows environment, it may end in .exe for executable. In a Linux environment, it's just got an executable characteristic associated with it. In a Mac environment, no clue whatsoever. But it's sitting out there on the storage device waiting for something to happen to it. When you double click on it, or you click a button to run it, or you select it from the menu, it becomes a process. You can run a program theoretically, if it's written right, or written with that intent, multiple times at the same time. Those processes can run concurrently. You can click and you can launch PowerPoint more than once. There are other programs you can run more than once. There are other programs that won't let you load them more than once. They're written that way. They're designed to only run one time. But as far as the operating system goes and the processor goes, it is possible to run the same program more than once. Each instance of that executing program becomes a process. Now, the process is, for the most part, living in RAM. It obviously may get swapped out because there isn't enough RAM. But typically, in theory, a process is loaded from a program and then lives in memory, runs as it needs to run or as the CPU decides it needs to run. A subset of a process is called a thread. That means a process can have multiple paths of execution running at the same time. You can have two processes or two threads in the same process. Threads can share some resources, but not other resources. And probably the most unfamiliar concept to us would be that of a program counter. That is a term for the current step of that program. What is that program doing right now at this exact moment in time? What machine code sequence, what CPU instruction is happening? That is where the program counter is. And then when that instruction is executed, the program counter is incremented to the next instruction, and so on and so on. That means that multiple threads running the same process can be in different points in the code. You can have multiple You can have multiple threads with their own data, also sharing some other data, and stepping through your lines of code at different points and executing different results. Every process is going to have at least one thread, and that's a good thought experiment for you to undertake. Why is it meaningful? Why does it make sense that every process has at least one thread? So think about that. The word deterministic matters to us. Deterministic means that given the same set of inputs, we will get the same output. If you put some money in the bank and you go check your balance, you want that balance to be the same every time you check it. If you play a video game and you turn it on, you want it to load the same way each time Or if it's got a previously saved game, you want that previously saved game to load at the same point so you can pick up where you left off. Deterministic behavior is one of the things that makes parallel programming difficult, because when threads and processes are sharing information, sometimes they get ahead of each other or they corrupt data unintentionally, and that causes the behavior to be non-deterministic. So when we study concurrent programming, we learn how to make our programs run the same way every time. If you haven't done this, it sounds silly, because up until now, you clicked run, you got the same results if you provided the same inputs. If you're running two threads at the same time in the same process, and they're stepping on each other, euphemistically, then you may not get deterministic behavior. Resources that the threads share, well, they're all stepping through the same code. Remember, two threads in the same process are sharing code. The only thing that they're not sharing as far as code goes is that program counter, meaning what they are doing at that moment in time. They could be in different points of the code racing through it independently. They can also share class level variables declared as static, meaning there's one instance of that variable because of the way we declared it, and all of the threads can hit that variable as they need to. You can imagine if they hit that variable at the wrong time and they corrupt each other, then you would have non-deterministic behavior. Now, this works really well for us because we don't have to have multiple copies of the program in RAM. If I have 10 threads racing through Firefox, I only need to have Firefox loaded one time, and each of the threads has its own program counter. That way I can do 10 different things in the same Firefox process concurrently. Threads can also have their own resources, particularly class level data that's not static. Any local variables. A local variable is any variable declared inside of a block. The block is an open and closed curly brace, meaning that if a variable is declared inside a method, inside a for loop, inside a while loop, inside an if-else construct, inside a try-catch block, those are all blocks because they use the curly braces, and they are not shared between threads. As an exercise, take a look at this snip and identify what is shared and not shared as far as variables go. Imagine I have two instances of this class. They're both running in separate threads in the same process. I have a variable called magic number declared as static, and it is a class level variable. That means that it is shared between all the instances of this class. Now this is a little misleading because there is a block there enclosing that variable. When we create a class, we put all the attributes of that class, the properties and methods, inside a block. But even though that little guy, magic number, is in a block, that's still shared because it's a static class level variable. The two variables below that, home planet and happiness quotient, those are not static. They are class level, so those are not shared. Inside the constructor, which is a block because it has curly braces around the code, there is a variable called delta, and that is also not shared. We end up with one shared variable between threads called magic number, and three non-shared variables: home planet, happiness quotient, and delta. Threads are managed by changing their state. When they are first created, when you double click on that PowerPoint app, that process with its own private thread is new, means it's not ready to run yet. It's being created. It's being loaded off the hard drive. Memory's being allocated. Program counter is initialized to the beginning of the program. And then, once all the creation operations are complete, it goes to a running state, or it may go to a waiting state. If the CPUs are all busy, then that thing can't run. It's just not possible. There's no place for it. And it will go to a waiting or blocked state. When everything is good to go, meaning that it's been initialized, it's not waiting for anything, then it goes to what's called the ready state. When it's finished, you click that big red X in the upper right hand corner. It goes to the terminated state, which means it's not quite out of memory yet. We're still allocating space, closing resources. There may be a file handle that has to be deallocated. You may have connected to a device that has to be turned off. When all those things are done, it finishes the terminated state and is unloaded from RAM. All the time as this is happening, new, running, waiting, ready, terminated, remember that program still sits on the hard drive. The program is now independent of this process that's being managed by the OS. The thread state diagram is pretty simple conceptually. A program becomes a process. It becomes new. That's the initial state of that process. Remember, that process has one thread, so at this point I can call it a process and we can assume that it has a thread. Everything's set up, it's good, the memory's allocated, program counter is initialized, all the local variables have been created as necessary. It goes to ready. It says, hey, put me into the CPU, coach. I'm ready to go. The operating system, which is the coach, says, hold your horses there, thread. As soon as all the other processes have a chance to run and when your priority comes up, we'll get you into the CPU as soon as we can. It sits in the ready state, ready, 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 waiting, waiting, waiting. Sorry, let's not use the word waiting. It's ready. When it does get loaded into the CPU by the operating system, it goes to the running state. It spends a very short time in there. Certainly not enough time for that process to complete. Eventually, the operating system says, you've been in there long enough, time to kick you out, put you into the waiting state. And it could be waiting for another crack at the CPU, or it could be waiting for an external event like a key press, or a device to respond, or even the screen to update in some cases. And then it spends most of its life cycling through ready, running, and waiting, ready, running, and waiting. Probably, if you were to study a process very closely, most of its lifetime is spent in ready and waiting between those two. Very little of the time is actually spent running. The CPU in most computers that sit on your desktop is idle the majority of the time. The CPU is not the bottleneck. When everything is done, when your program decides it's finished, it reaches the bottom of the main, so to speak. The operating system sets it to the terminated state, cleans it up, and it no longer exists. It's just a happy memory. The OS, in conjunction with or at the request of the JVM, manages the thread states. You don't have the option of making your thread stay in the CPU for an hour. Some operating systems, yes, but not the common operating systems that we use today. Because if the programmer could control the thread state, then whoever got there first would never leave the CPU. And we'd have a really slow, messy experience with our computer. The operating system has a much better algorithm for managing the thread states and deciding when a thread has had enough CPU time and when it needs to go back into the CPU again. Another term that's important to us is atomic. As developers, we have to identify sections of code that cannot be interrupted under any circumstances, else they will cause data corruption eventually. When we identify an atomic piece of code, we have to take steps to make it uninterruptible. And all that means is we're telling the operating system that once you start this little bit of code, don't let any other thread go through that section of code until I'm finished. It's really a function of the operating system monitoring the program counters and making sure they don't overlap each other. And let me try to plant a very important seed. If I have a declaration of a variable and then a bunch of code, this is just rough pseudocode. Somewhere in my code I have this, x equals 42, just for the sake of argument. That is not an atomic piece of code. It can be interrupted midway through. Even though it looks to us like it's one simple line of code, what could possibly go wrong? It's an assignment statement. Well, that actually breaks down into multiple CPU instructions. Therefore, it's not atomic in and of itself. So don't write code thinking that you can write it small enough or fast enough or cheap enough so that it's always atomic. It's not. And we'll talk about that as we go along. But you cannot, without external intervention, without adding some logic to this, ever assume that your code behaves in an atomic fashion. Here's the slide summarizing what I was just harping on. A chunk of code cannot be assumed to be atomic unless you program it that way. It doesn't matter how small that line of code is, how small that chunk is. X equals 42 looks completely harmless. What could go wrong there? Well, there's plenty of places in that statement that could be interrupted by the operating system. That thread gets shuffled out of the CPU. Some other thread comes in. And if it goes through the same program counter, we could have all kinds of problems. Hopefully you realize by now that we want our threads to be deterministic. We want the code that we write to behave the same way given the same set of inputs. Now our inputs are going to change. That's part of testing, and that's part of the way programs are supposed to work. They accept varying inputs, but when they produce different results for the same input, then we are writing non-deterministic code, and that could be very bad for us. One easy way to solve this problem is to just write everything serially and not write any parallel code. However, that makes our computers almost useless. We can run one program until it's done, and then another program can run. Nobody would enjoy that. We have to learn then how to write parallel programs, concurrent programs, multi-threaded programs, any way you'd like to describe it. To be specific, our process, which contains one or more threads, runs in one or more cores if the CPUs have more than one core. Otherwise, they run in more than one CPU. Now, what we've seen today is that there is a ambiguity between the word CPU and the word core when we talk about programming. Most of the computers we pick up today, even our phones, have multiple cores. And from the perspective of your code, that looks like multiple CPUs. Sometimes it's not, sometimes it is. But we're going to use the term CPU and the term core as pretty much the same thing in these discussions because we're concerned about it from a software perspective, not a hardware perspective. If I launch a thread, I don't care what CPU it's in. I just know that it's running in a core in some CPU. To get it even more complicated, there are CPUs that are asymmetric, meaning that the cores are different. Some cores do some things, some cores do other things. But in our world, all the cores are the same, which would mean it's symmetric multithreading. We've realized then that parallel programming has become a big deal, and if you pick up a modern PC, a modern Windows computer, Apple, Linux, they all support this technology. And even the cheapest smartphone that you're going to pick up probably has multiple cores in it. Probably one CPU, but multiple cores in that CPU. The video card manufacturers realized pretty early on that their cores, which are optimized to manipulate video, could also be used for other things. If you've done any Bitcoin mining or any crypto mining, then you've probably run into software that you can download to use a video card to do computations for crypto mining. Now, those things weren't designed for that. They were designed so you could play Red Dead Redemption or Mario Kart or whatever, but people adapted those cards because they have thousands of cores and they use them to do other things in parallel. That drove up the price of a lot of video cards. I'm not big into that arena. I can't tell you what the state of it is right now. I can tell you, though, that NVIDIA, among other video card manufacturers, offers programming tutorials, workshops, environments that lets you learn how to do parallel programming on their card. A lot of it's going to be in C. If you know some C, then if you know a lot of C, let's be honest, you could jump into one of these tutorials. Again, highly recommended that you at least investigate this, and you may find something that's at your level. You may be able to dramatically improve your skill set as a developer by learning some parallel programming on a graphics card. But I'll tell you what, it's not easy. The good news is that Java, the JVM, the Java programming language, in conjunction with the operating system, lets us do multi-threading in a fairly straightforward way. It can get complicated, you still can make mistakes, but the foundations are there. There are also many ways to do the same thing. So what you see on these slides and what you see on websites will be different perspectives on accomplishing similar things. More terminology. I encourage you to look up all these terms and get a good, firm definition in your mind of what they mean, because they will come up in job interviews and in the work that you do. I attended a workshop in 2019 in North Carolina that was dedicated to teaching parallel programming. We spent a week learning different technologies and exchanging ideas with each other. One of the things that they told us, this really resonated with me, was a study was done with computer science students, and this is not IT students, but computer science students. They have a course called CS0, Computer Science 0, which is their intro course. The study was performed against two groups. One group of students who had not taken CS0 and another who had taken it. Remember, in that course, they're going to learn the basics of computing. They're going to learn some programming, probably Java, maybe Python, maybe C, C++. And then they're going to come out of that one semester long course with an understanding, however broad, of how computer science works. And they'll have written some code, they'll have studied some concepts. The question applied to the students during the research was, you need 10,000 peanut butter and jelly sandwiches. How do you get them? The caveat was you have an unlimited amount of resources. You can get whatever you need in the real world to do this job. The students who did not take, well, let's back up. The students who did take CS0, who'd completed that course successfully, their solution was get a knife, get a jar of peanut butter, get a jar of jelly, get 2 pieces of bread, put the jelly on one bread, the peanut butter on the other bread, smash them together. You have a sandwich. And then they put a loop around that to repeat 10,000 times. Okay, that makes sense. You get 10,000 sandwiches. The people who had not taken CS0, who had not been exposed to the fundamentals of computer science that way, their solution was or tended to be get 10,000 people and have each of them make a sandwich. That's parallel programming. And that's a dramatic illustration of what we need to teach. Because if your mindset is serial rather than parallel, you're going to come up with different solutions to the same problem. Operating systems are, as I said, inherently multi-threaded. Without them, we would be in big trouble because we'd have 8 cores, but we'd only be able to use 1. Therefore, designing an OS from the ground up that's multi-threaded is crucial. And that's going to be Linux, Windows, Mac, plenty of other ones as well. There's also a subset of multi-threaded operating systems called real-time operating systems, or RTOS. Windows, Linux, Mac, none of those are real-time. They run very quickly, but they run as a function of the CPU and the RAM and the bus speed, and they are not behaving in a real-time fashion. We're not going to get into the details of that, what real-time OS means. If you want to know more, visit me during office hours. I'll tell you all about it till your ears bleed. If you want to see your computer multi-threading, just bring up the task manager. You can see that in this little snip, there is a process called service host, SVCHOSD. That is probably the most researched process in Windows. That's probably been Googled by more people than anything else because it looks very disconcerting when you check out the task manager. You see numerous instances of that little thing running. So service host has been launched multiple times on this computer, and it's doing different things in each of those processes. And people want to know, why is it doing that? They get on, they Google service host, svchost.exe, and they find out that, yeah, it's probably okay. It's probably Windows using that very flexible program to do multiple processes. And of course, there could be some malware in there, who knows? But I think most people, after a few minutes of searching, they realize it's probably okay. That snip is really old. I'm thinking that's Windows XP. I don't know. It's an old snip. You do have Task Manager on your machine though. I think I have mine running on my current machine, and I have a desktop recorder running to capture this video. It's consuming a huge amount of CPU time. If you look at my screen, I hope you can see that almost half of the CPU time is given over to this capture software. Dramatically huge numbers. Very rarely are you going to see a program that takes up that much CPU time. And this has to be because this capture program needs to be grabbing my video and my audio and saving all that to the drive in a streaming fashion. And that does take resources to do that. Also, you can see I've expanded the Firefox process, and I can see that I have about 10 or 15 threads running through Firefox right now. Also notice that Windows uses the term task, and I don't know specifically how a task maps to a process, but I think they are the same thing. It's called the Task Manager, but there is a tab called Process. Now my computer is a Aspire E5 575G, which when I bought it was really cool, and I still love it to death. And it has an Intel i5 6200U. Now that doesn't mean a lot to me. I'm not a CPU geek anymore like I used to be. But I looked it up. Intel assures me that the i5-6200U has two cores. That's two physical processing units inside one CPU, one chip, I guess. Two cores on the chip. And then each core has four threads. I'm sorry, each core has two threads, or let's say up to two threads, meaning that the core is designed so that it can run two threads at the same time. And in some instances, this is called pipelining. If you study computer science or computer engineering, it's a topic you'd have to cover because somebody invented a way requiring specialized hardware and software to run two programs through the core at the same time. Intel calls that hyperthreading, I believe. And other manufacturers of CPUs might call it something else. But when I taught computer engineering or architecture courses, we called it pipelining. That's all we care about right now is just an overview of the terminology. I don't care how Intel does it or AMD does it or Motorola does it. I just know that it works and that I can write Java code to leverage the ability to make it look like I have four cores. And that's pretty cool. The two physical cores inside one physical CPU, each of the two cores virtually or behaving like they can have two programs running at the same time. Here's some Java code. There is a class called thread. How about that? It models a thread. How about that? So we've kind of skipped the program and process steps and gone directly to the thread step. We're going to think about our work in terms of individual threads. And a thread can be the only thing running in a process, or there can be multiple threads in a process. It doesn't matter though, we're just focusing on the concept of a thread. The JVM worries about the process and the program in conjunction with the operating system. All you have to do is extend the thread class in a new class of your own choosing. I called it my thread. And then all you have to do is write a public void run, which overrides the run class in the thread class. So you're overriding a method in the base class. Inside the run class, just put the code that you want to execute when this thread starts. And this is interesting to us because we don't have a main anymore in this thread. The entry point for the thread is run. We'll still have a main that launches this thread, but the thread won't have a main. It'll just have a run. Slide 25. Once we've created, declared, and instantiated an instance of our myThread class, we call start. We don't call run. We didn't even write start. Start is inherited from the base class. Start is in thread. MyThread invokes start. That tells the thread class that whenever you're ready, whenever it's convenient for you, execute the run method in our object. Again, this is completely out of your control once you've called start. Your thread might not run. The run method might not execute for several milliseconds, or who knows. It's a function of when the operating system gets to you, when there's space in a core, and when everything else that needed to run that had priority over you has already run. You want a multi-thread? Just call start over and over and over. So each time you invoke start, it will call the run method on your thread object. That doesn't mean all is immediately well. I mean, you may have misprogrammed something and they may interfere with each other or crash or lock up, but simply invoking that start method eventually invokes the run method on each of those thread objects. Let me talk about sleep briefly. There is a sleep method in the thread class that you inherit when you create your own thread class. If you want to pause the thread, just call sleep. The parameter is the number of milliseconds that you want that thread to pause. Now what this means is the operating system takes the thread out of the CPU, and at least that much time must elapse before it can come back into the CPU. You're not bogging down the system, so it's not sitting in the CPU spinning for that many milliseconds. This is not, and let me underscore that, not a way to make things program concurrently. This is not a tool for getting around concurrency problems. This is not a tool for writing good, robust, deterministic parallel code. This is a great tool for teaching and testing. It is not a tool for writing deterministic code. Don't use it as a crutch. Oh, if I make this thread sleep long enough, it won't interfere with any of the other threads. Wrong, wrong, wrong. Don't do that. You may as well just start writing serial code again and give up. Thread is easy to use because when it wakes up, it throws an exception. You just wrap it in a try-catch block. Your code hangs up on the sleep and it stays there until the number of milliseconds has elapsed. Nothing to it. It's deceptively easy and deceptively scary to use it incorrectly. The next thing we'll do is load in our project, take a peek at it, discuss it together. I have mine loaded into Eclipse. I have a main, which we'll talk about in a second. I have a myThread class, which inherits from the Java thread class. If you hover over thread, it tells you that it's java.lang.thread built into the Java language. And I don't even need an import statement, do I? How about that? That's pretty neat. Okay, as I said, there are many ways to do these different things. This is one way where we create an instance of a class that inherits from thread. So we'll demonstrate basic concept with this, and if you scan the interweb, you will see other ways of doing it too. This is our run method. The run method is the entry point for the thread. There's no main anymore. All our code needs to go into run. And then of course you can invoke methods from here. I'm invoking println from the run method. I'm invoking sleep from the run method. And I could write other logic that creates more classes and does all kinds of amazing things. So your code doesn't have to be in the run method, but it has to be invoked out of the run method. So that's your starting point. You can also see that there is a run method in the thread class, in your base class. You're just overriding it. So that's an example of overriding a base class method with a method in the derived class. What does this little guy do? It prints out a message, hello from the thread, whoop-de-doo. It goes into a loop. It prints out a value 25 times along with a friendly message. And then it goes to sleep. No reason for that, just to make the thread not die so quickly. It sleeps for 50,000 milliseconds, which is 50 seconds. Remember, that's not a crutch for writing good parallel code. This is just here so I can keep the thread alive for a little longer and talk about interesting things about parallel programming. And then finally it prints a message that the thread is exiting. Alright, that's what the run method does, not much to it. If you look at the main's even smaller. Instantiate an instance of the myThread class, the class we just looked at. Call the start method. What does start do? Start invokes run. We created a run method in the myThread class. There it is. It's fat, dumb, and happy. And then we call start. The operating system, in conjunction with the JVM, decide when it's going to call our mythread.run. After that, it immediately continues. So nothing blocks our code right here in line 19. It doesn't wait for it to start. It doesn't wait for it to finish. It immediately blasts ahead. It goes and prints 25 messages. The point being that these two little blocks of code, the main and the mythread.run, will be in separate processes. And they will both be trying to use the console window to generate output. Let's see what happens. This is going to be so exciting. Nothing in the console window right now. Click Run on the main class. There's the output. Your output might not look like mine. Your output might not be in the same order as mine. Now mine, if I look at it closely, apparently everything in the main thread finished before it even started that run method in the thread object. It finished the main. It got all the way down to here before the thread even got kicked off. That's what happened to me when I ran this. Let's run it again. What happened this time? Pretty much the same thing. Let's run it again. Pretty much the same thing. I'm going to make this console window bigger just so I can see what's going on in there. Finally, after running it about 5 times, I got a different result. Look what happened closely in my console window. There's output from the thread interleaved or mixed into output from the main. Now we're seeing an example of the JVM ran part, looks like I clicked it too many times. The JVM ran part of the main, and then part of the thread, and then part of the main, and then part of the thread. I can't get it to do it to repeat again. But you saw it there for a moment. Let's see. Maybe I'm just, let's try this. Ah, yeah, it's the sleep. Okay, I got ahead of myself because it's actually sleeping 50 seconds between runs. So I kind of got confused there, but let's just, I've killed all the processes running now. Let's try it now. Okay, so now if I'm going to have to wait 50 seconds. I didn't do that before. I got too excited. See the little red button there? I'm still waiting for this sleep to complete before that thread finishes. And I'm just sitting here waiting. Ha 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 ha, having a good time. Waiting for the 50 seconds to expire. Anyone know any good jokes? What did the dolphin say when he walked into a bar? I don't know what the punchline is. Anyway, it's about to finish, I'm sure. So we're just waiting for that sleep to complete. At the bottom of the console window, it should say exiting thread. There it goes. Now, in my previous demonstration a few moments ago, I just got excited and kept running it over and over. So let's take out the sleep now. Let's take out the sleep. Comment out line 20 in the myThread class. Back to the main, run the main. Now we should get some gibberish here. If we do this enough times, just keep running it until There we go. I had to run it about 4 times. But now I see that the threads have what interleaved with each other in competition to write to the console tab. There's some output from the main, and then there's some output from the thread. Therefore, we can kind of tell that the two threads are running at the same time in a non-deterministic manner. Remember, every time we ran it, we are under the potential that we might get different results. So non-deterministic code. If I run it again, it might line up this time. If I run it this time, it got all the way to 22 in the main, and then it started up with 5 in the thread. Non-deterministic code. Back to slide 29. Note that there is a example of an is-a relationship in my project. We've talked about is-a and has-a, and that tends to be something that confuses people. In this example, in this Eclipse project, the myThread class is a thread object. So it's an is-a relationship between myThread and thread. And that is demonstrated if you look at mythread.java right here. That's an is-a relationship. MyThread is a thread. Thread is the base class. MyThread is the derived class. Using the other terminology, thread is the superclass and MyThread is the subclass. We don't have a has-a relationship in here. That's all we have is an is-a. Critical section of code. Remember, sometimes in our program we realize that there is a set of code, usually not too much code, that cannot be interrupted. And that is considered to be what we say atomic, meaning that it has to be one piece. It has to run before any other program can get in there and run the same block of code. And along with that, it also cannot be interrupted. That's a toughie because eventually you're going to get swapped out of the CPU. But the operating system will make sure that even though you are not in the CPU, that there is nobody else interfering with what you were trying to accomplish. So the term interrupted is used a little bit loosely. Mechanically, you are interrupted. Mechanically, you're out of the CPU, you're back to waiting mode or block mode. But the operating system and the CPU know all the things you were doing, and they won't let anybody else get in your way. One way we can do that in Java is by writing the synchronized keyword around that critical section of code. It ends up actually being pretty easy then. Once we've identified the critical section, that's the hard part, programmatically making it critical, making it atomic, is accomplished just by making it synchronized. There are different types of parallel programming problems. One of them is called a race condition. This produces non-deterministic code. We have two threads in the same process. Remember, these threads are sharing code, but they're not sharing program counters. And these two threads, when they go through the same part of the code, get in each other's way, causing a problem and creating non-deterministic code depending on the order of the steps they go through that code. And a classic example of this is making a deposit at an ATM. We have two people, John and Mary, two anonymous people who share an account. So they work together, they whatever, and they have access to the same account at the bank. They're the same thread. They're the same process but different threads. And each of them wants to make a deposit. They both got paid. They both sold something on eBay. They both went to Half Price Books and traded a bunch of books. I don't know, but they each have a little bit of money. Each of them represents a thread in the same process. The process would be the program running on the bank's side that computes these deposits. So John has initiated a deposit, that becomes a thread. Mary has initiated a deposit, that becomes a thread. The problem is that it doesn't matter who goes first, because whoever goes first may still get interrupted depending on the operating system and the JVM. So it's not a race to see who can go first. It's a race of the two threads to see who can go and finish first. But that's never going to happen. We have to write our code so that it does happen. We have to write the code so that John's thread doesn't get interrupted in the critical section and Mary's thread doesn't get interrupted in the critical section. When you're new at this and you're thinking about the problem of a race condition, your first inclination is to make the entire program the critical section that cannot be interrupted. Well, that's just serial programming. That's not parallel anymore, because the whole thread has to finish before some other thread can enter that block of code, and that's not the way we want to do things. Therefore, it's important to reduce the critical section to the smallest chunk of code possible so that most of it can run in parallel with other threads. This is a computer science problem from a math perspective. There are 4 conditions that have to be met. Notice that there's no programming on this slide. We can talk about parallel programming and race conditions in theoretical terms as computer scientists, and then we apply those terms that the computer scientists have come up with in our program. The 4 conditions that are necessary that the computer scientists came up with are: no processes may be simultaneously inside their critical section. So that, again, that's the program counter. Each thread has its own currently executing statement. Each thread has its own program counter. If there's a critical section that's been defined, only one thread can have a program counter inside that critical section. Number 2, that's the one I pounded you about a few minutes ago. You can't assume the CPU is really fast or really slow. You can't put a sleep statement in there. You can't look at the code and say, oh, that's so fast it'll never get interrupted. Refer back to that little code snippet I gave you earlier. This is about the smallest piece of code you can have, x equals 42. That could be interrupted at several different spots. Therefore, you cannot assume that the CPU is so fast so that a line of code will never get interrupted and swapped out. The third requirement for avoiding race conditions is that this should say thread. No thread running outside its critical section may block other threads from entering the critical section. And that creates a deadlock where nothing can happen. The fourth is no process should have to wait forever to enter its critical section. And that's a function of the third requirement here. So you can't lock me out of the critical section forever. If you're programming a thread and I come along in another thread, you have to finish that critical section so I can get in there. You can't hog it. Here's a literal representation of the race condition. John and Mary have 3 steps to go through. The steps are identical, the amounts are different. John wants to put in $500. Mary wants to put in $500. She makes more than John. John wants to put in $100. They're depositing to the same account. The same account. John is at one ATM in a parking lot next to a Kroger. Mary's at another ATM downtown after lunch. And for some weird, wacky reason, they hit deposit at the exact same time. They're on the phone with each other and they say, "Oh, I love you, John. I love you, Mary. Let's deposit our money at the same time." And they both hit go. Well, that starts the race condition. And if you execute these three steps in different combinations, you will get different balances at the end. And I encourage you to get a piece of paper and do this. If you execute J1 and J2, read the account balance on John's side, increment the balance by hundreds, that's J1 and J2, and then stop and then execute M1, M2, and M3. Read Mary's balance, increment the balance by 500, write the new balance back to the file, and then come back and finish John's process or John's thread. You'll find out you get a different result than if you execute them in the second suggested sequence, M1, M2, M3, J1, J2, J3. And if you do that on paper, you will see dramatically that a race condition is really easy to visualize. Now, writing this in code is also easy. You just don't define a critical section, that's all. Eventually, if you run these two threads concurrently enough times, you're going to get corrupted data. But what you're also going to find, and this is wrong, this is misleading, is that the CPUs are so dang fast that it's unlikely that they're going to interleave, and it's unlikely you're going to get anything but M1, M2, M3, J1, J2, J3. So that's why the sleep comes into play, and sometimes we build in a delay just to make the race condition appear so we can all see it. That's why sometimes you'll see the sleep when you're looking at academic code, demonstrator code, but you don't see it in production code. It's just not a way to make things deterministic, not a good idea. Here are some advisory guidelines for you. One thing that most people don't realize is that the output that goes to the console is in its own thread. It's bopping along there and you don't even know it. It's running in the background in a different thread. So just because the order of output is different in the console window doesn't mean that the threads execute it any certain way. Don't get misled by what you see in the console window relative to the order that things show up. So just because it reads from top to bottom doesn't mean it took place from top to bottom. Let's look at John and Mary. I have provided for you two versions of John and Mary. John and Mary deterministic, John and Mary race condition. Let's look at John and Mary race condition first. This is the one that's fun because it's broken. Don't worry about the package name. It looks a little bit weird. Let's look at the main. The main calls a method called demo. The demo method creates two threads and starts the threads. That's all it does. And then we're going to look at the threads. There is something new here in the main. After it starts the threads, you have to be careful because if you race through the main and the main finishes, remember the main is in its own thread now, then when the main finishes, the JVM kills all the other threads that you may have started. Therefore, you have to do something called a join. And in this case, I have to join to both John and Mary threads, the John thread and the Mary thread. And that way, I wait for both of them to finish before I let the main finish. If you don't do that, you're just going to get confused because the main zips through before John and Mary can finish. Therefore, you don't get the complete results. So take a look at the join method of the thread class. Google that, read about it a little bit. And remember that if you have a main, if the main finishes, any threads that you've launched will also be killed right away. They're not going to get a chance to finish. That's the way we've architected our program. There are ways around that too. That's just the way we did it. Okay, let's look at the make deposit. Now we got a problem because this is where John and Mary want to put in their hard-earned money into the bank. The run class calls a method called doIt. The doIt class just makes the deposit. I just modularized all this stuff. Here's the doIt method. And right here is what needs to be synchronized. Okay? Grab a copy of the balance, add money to the account, add money to the balance, I'm sorry, and the third line too. So this line also needs to be part of the atomic section, which we refer to as critical. So right here is where we're going to have a problem. If this thread doesn't get to finish those 3 lines of code, ignore the sleep, then we're going to have a race condition potentially between 2 threads going through this code. That's where the race condition comes into play. And those are very harmless looking lines of code, aren't they? What do you see there? Line 37, a variable declaration and an assignment statement. Harmless. Line 38, adding 2 numbers together and assigning that result to a variable. Harmless. What could go wrong there? Line 41, assigning one variable to another. Harmless. If you look back at slide 34, those are the 3 steps in that representation. J1, J2, and J3, M1, M2, and M3. Those 3 lines of code represent those 3 steps. That's all I did. Enough of this. Let's go run it. Remember, the main kicks off 2 threads that want to do exactly the same thing. One of them wants to deposit $100. One of them wants to deposit $500. That's all they do. Let's bring up our console window. Clear it out. Why not? Click Run. The final balance is 542. That's a problem because John and Mary deposited a total of $600. So how in the world did we not have at least $600 in the account? Well, it looks like we lost John's deposit because we started with $42, just arbitrarily. Everybody should have $42 in their account. We tried to make 2 deposits. We ended up with $542. And that print statement comes from the main all the way at the bottom. After John's thread is finished and Mary's thread is finished, we have $542. The bank lost $100 of John's money. And that could cause all kinds of relationship problems between John and Mary. That could be a real deal breaker if Mary wonders where that money went. Let's run it again. 142. All I did was run it a second time. That's all I did. I didn't change any of the code. I changed nothing. Non-deterministic code. This time we lost Mary's deposit. Now John is suspicious of Mary. What's she doing with the money? Where did it go? Real relationship problems could result, and it's all the fault of you, the programmer, writing non-deterministic code. So take your work very seriously. The fate of John and Mary's relationship depends on what you do. Let's run it again. 142. Eventually, there's 542. Eventually, maybe we'll get 642, which would be a successful process of their two deposits. We may never get it. Who knows? We seem to be flipping back and forth randomly between 142 and 542. If you go back to the make deposit class again, you'll see the sleep. And the sleep is in there simply to cause these two threads to interfere with each other. Because we're using a modern machine and a fairly reasonable programming language, and we're using a very small critical section, it's possible that the critical section races through for the first thread and then races through for the second thread, and they never interfere with each other. Therefore, I put a little bit of sleep in there so that one thread starts, goes to sleep, the other thread has a chance to finish, and then they interfere with each other. So if you don't like that, if that seems like cheating to you, you can take out that line 40. You can take out that random sleep. I mean, that is real world, because in the real world, computers get interrupted and they take time out from doing what they were doing while the operating system swaps in another process. Something else happens. Maybe a communication slowdown, maybe a internet slowdown, who knows. But if you take that out, rerun the main, there's the right answer. If you run this over and over and over, I promise you, eventually you'll get a non-deterministic result. It just might take you a year, because these critical sections now are so small and so quick that they don't interfere with each other. But that doesn't mean you've written deterministic code. That just means you got lucky. No assumptions may be made about the speed or number of CPUs. Don't fall back on the old crutch that, oh, my computer's fast enough, those threads will never interfere with each other. The other project is called John and Mary Deterministic. You probably already guessed what that has in it. I'm going to close the code tabs from the first project. Let's look at John and Mary Deterministic. The only thing we're going to even care about here is the fact that I synchronized it. Doing that tells Java, which then tells the operating system, this little bit of code cannot be interfered with by other threads. And that works. We can run this now and leave the sleep in there to cause some randomness, and it will always give us the right answer, 642. I expanded this one to not just run once, but to run a whole bunch of times, just to prove that yes, it really does work. That way you don't have to sit there and click the button over and over and over. And it does work. Okay? The reason this one gives a different answer, not 642, rather 1642, is because I'm spawning another 1,000 threads, each of which deposits $1. In this case, then, this program is actually doing 1,002 concurrent threads. Theoretically concurrent. They probably finish well before all of them are running at the same time. It just shows that I can put a little bit of stress on my algorithm by asking it to do 1,002 theoretically concurrent deposits and still get the right answer. But I wasn't happy with that. I ran that test of 1,002 deposits 10 times. And each time it runs, I get 1,642, which is Bob and Mary's 500 plus 100 plus 42, and then 1,000 deposits of $1 each. And I encourage you to stare at this and figure it out, take a look at it. Let me know if you have any questions. Come see me during office hours because it's all a little bit new, but it's extremely important. It's well worth your time to look at. It's well worth your time to try to start to develop a parallel mindset for everything that you do. If you're presented with an algorithm, how can I parallelize this algorithm? And sometimes you realize it's not necessary, but then sometimes you realize, hey, I can do this a lot faster if I break it up into parts that can run in parallel and take advantage of all these CPUs that I have. Slide 38, there's that synchronized keyword that I showed you in the code. I'm creating a block, and inside that block, it's labeled with synchronize. Nothing can go in there. The program counter cannot enter that block unless nobody else is already in there. Of course, it's easy enough just to take out the synchronized logic to demonstrate non-deterministic behavior. No problem there. New concept. We have a term called thread safe. You're going to hear this term a lot, and you should ask yourself about thread safety all the time. Thread safe means that the data structure or the code I'm referring to can be run in multiple threads at the same time. So you can say this code is thread safe, this data structure is thread safe. There's even a threadsafe.org website. I have not investigated it, but it sounds really cool. Maybe you want to join. Thread safety is crucial in writing deterministic code. We already saw how to add the synchronized keyword to create a thread safe block of code. The other consideration then, along with logic, is data structures. Are there data structures that I can use in my program that aren't going to interfere with each other and that will behave in a deterministic manner? Not all data structures are thread safe. We've spent a lot of time studying Java array lists. Well, guess what? They're not thread safe. Pretty scary. Now, if you want to write thread safe code with something that behaves like an array list, you can find something called a synchronized array list. How about that? But just as it is by itself, if you try to run and manage data in a multi-threaded manner using array lists, eventually you're going to get in trouble. So file that term away in the back of your mind and look for data structures that are thread safe. The downside is they take longer. You have more overhead built in. So a thread safe data structure over time will be less efficient than a non-thread safe data structure. But hey, that's how it is. You got to give up something to get something, right? Udacity. Here's a place where you can go to learn all you'd ever want to know about parallel programming. I think it's all in C. There may be some other courses added that I'm not aware of. But again, it might be worth your time to take a peek at and see if there's something you can use to build your skill set. In closing, I mentioned that I have created in my GitHub site a repository that demonstrates thread-safe data structures versus non-thread-safe data structures using array lists. And I would suggest to you that you download this, clone it, you know how to do that, run it, take a look at the results, screen snip the results, and write me a paragraph about what you learned, and I will give you extra credit for that exercise. Again, clone that project to your machine. You don't have to fork it if you don't want to. Run it, snip the results, study the results, study the code, write a paragraph about what you learned, what's going on in there, and then submit that to me. I will give you extra credit. With that, I will say thank you very much. Have a good day.